ahead and get started then.
Yep, you're ready to start, Christina.
Okay, awesome. Thank you, Angelica. So hello, everyone. My name is Christina Chang, and I'm the project manager for this year's Spaceport America Cup rocket team. The team consists of 14 engineering seniors, 11 of which are mechanical engineering majors, and 3 of which are electrical engineering majors. Since the Ares 6 team from last year was unable to launch a competition due to the COVID-19 pandemic, we have inherited many of their designs and have named the 7th iteration of the rocket Ares COVID to keep the spirit of Ares 6 alive, as you can see by the logo that the team designed in the top right corner here. So for a little bit of background on the competition, Spaceport America Cup is the largest intercollegiate rocket engineering competition in the world and is hosted in New Mexico during the summer. The goal of the competition is to design a solid hybrid or liquid propulsion system that will propel a student-built rocket to either 10,000 or 30,000 feet. The CSU Ares team will be competing in the 30,000 foot category with a liquid propulsion system this year. Judging is based on the scientific merit of the experimental payload on board, how close the rocket comes to its predicted apogee, and how successful the rocket's recovery system is. For an overarching design summary, our rocket as it stands is predicted to have a 6-inch diameter and be about 18 feet tall. The experimental payload we will be implementing is a 360-degree camera that will capture real-time images of the landing site upon recovery. Our team has been split into 3 sub-teams to delegate tasks more efficiently. The controls and payload team is responsible for remote fueling and ignition, launch control operations, and all telemetry systems. The airframe and recovery team is responsible for building the structure of the rocket, which include the nose, body, and fins, and also ensuring that the dual deployment parachute recovery system is activated at the correct altitudes. And the propulsion sub-team is responsible for the testing and calculations that go into the student research and developed propulsion system that actually makes the rocket fly. So going a bit more into detail in the controls and payload aspect of the rocket, all of the electrical engineers on the team are on the controls and payload team to assist in electrical configuration and circuit calculations. They have implemented different types of pressure transducers to track fueling, remote controls to control oxidizer flow, and different types of components to ignite the pyro valve and preheater. The controls team is responsible for the software and hardware that allows for a safe launch, deployment of parachutes, and GPS tracking. The majority of these electronic components are housed in the electronics bay located in the body of the rocket, and the block diagram on the left shows the electronic functions on an elementary level. The launch controller for this year's team is being developed using physical hardware that consists of protected switches for filling and arming that will be capable of reliably transmitting signals from 2,000 feet away from the launch pad as the competition requires. The in-flight operations consist of the controls that determine when to separate the airframe and initiate the parachute deployments. The controls sub-team has implemented 2 commercial off-the-shelf controllers to accomplish this task, where the redundancy ensures reliability. And a student researched and developed flight computer will be used for telemetry transmissions during flight. This flight computer will be capable of GPS transmission to locate the rocket after recovery. And the heart of the flight computer is a Raspberry Pi that will collect data from a sensor array, process and log that data, then send it in an automatic packet reporting system format to an amateur ham radio transmitter. The entire system will be contained in a single custom printed circuit board and radio transmitter. As for the airframe and recovery sub-team, the recovery system consists of 2 parachutes, one that deploys at apogee at 30,000 feet to slow the rocket's descent, and another that deploys closer to the ground at about 1,500 feet to ensure that the speed of touchdown is safe. These parachutes will be released by black powder reactions, splitting the rocket into different sections. The airframe will be made of fiberglass with an aluminum nose cone tip and clipped delta-shaped fins for the most efficient aerodynamics. Aside from considering efficiency, the structure of the rocket must also be designed to protect the internal components and prevent structural failure. The nose cone will contain the payload. The body will contain the main and drogue parachutes for recovery, the electronics bay, and the propulsion system. The fins attached to the rocket must be able to withstand drag forces and stabilize the rocket. Additionally, the body needs to be as light as possible for maximum efficiency of the propulsion system. The separation of the rocket will be initiated by an electronic match that will ignite a black powder charge contained within burst disks. And the force from that explosion will cause shear pins to break at separation points, therefore separating the rocket effectively. And finally, the propulsion subteam is working on the bipropellant liquid propulsion system using liquid ethanol as the fuel and liquid nitrous oxide as the oxidizer. The fuel and oxidizer will be housed in concentric tanks to reduce the amount of weight of the system. Calculations have been run both by hand and through MATLAB to nail down the amount of each substance needed, as well as to estimate the predicted trajectory of the rocket. The propulsion system as a whole consists of the fuel tank, oxidizer tank, valve system, combustion chamber, and nozzle. In order to reach the desired apogee, the propulsion system must be designed for maximum efficiency to minimal weight. The weight of the system has been optimized by using a transient MATLAB model, thus determining the minimum amount of fuel required to reach apogee, the optimum nozzle geometry, and the tuning of the valve system. The valve system for the rocket is the system that regulates the amount of fuel and propellant that flows into the combustion chamber, which is controlled by two pistons that are able to control that flow. And that's what's pictured on this slide here. So that is a very basic outline of what the team has been working on up to this point this year. We are planning our first subscale launch at the beginning of March and hoping for a successful competition, COVID permitting. As you can imagine, with a project this large, there are many points of integration between subteams, so individual subteam members are often able to experience the work of other subteams. And thank you for listening. If you have any questions, you can always feel free to email csurocketteam@gmail.com.
Awesome. Thank you so much, Christina, for presenting. Next, we'll have the NASA Robotic Mining Competition, and Connor will be presenting for this group project.
Awesome, thank you. So we're the NASA Robot Mining Competition team, and I'm Connor Worrell. There's three other people who are going to be helping me present here, are also on the team. They're going to be introducing themselves kind of as we go through this presentation. We're going to tell you a little bit about the competition itself and then our solution to the competition. So next slide, please.
Hi, my name is Lex Policita. I'm on the controls sub-team for the NASA Robotic Mining Competition. So the project overview kind of is that NASA Robotic Mining Competition was created by NASA to work towards their goal of landing astronauts on the moon by 2024 so that they can establish a lunar colony soon thereafter. There is a tremendous value in establishing a lunar colony on the moon, but it comes with high shipping costs. So it costs about $1 million for every kilogram sent to the moon. So the competition was created to kind of find a way to utilize the resources on the moon instead of sending them to the moon. And so there's also a limit on the mass of the robot to account for this high shipping cost. Next slide. Okay, and so the competition has 3 phases: the design, the build, and the mining phase. The design phase was all of last semester and consisted of fully designing the robot and creating a functioning CAD model. We're currently in the middle of the build phase, and we're working on building our robot and testing everything that goes along with it. The 3rd phase was canceled this year due to COVID-19, but it involved the in-person mining competition in Florida. The NASA deliverables that go along with this competition are various design and building deadlines, as well as different reports that we have to submit to NASA. Some background on the next slide. So because NASA wants to establish the lunar colony, they needed to figure out a way to utilize the resources on the moon instead of bringing them to the moon. And so they found out that there's some ice underneath the layers of the moon. And so the essential resources we can get out of this is water and oxygen. And so the competition was created to mine for that regolith under the surface of the moon, and it can be melted down to form water and separated into hydrogen and oxygen. And the figure on the left shows the depth of the simulated ice regolith in the competitions in the past. And so we have to mine down through the surface to get to this regolith.
Hi, my name is Kyle Chigarelli. I'm a mechanical engineer and I'm on the mining sub-team for this project. So just a little bit more background about the NASA Robotic Mining Competition. It started back in 2010 and it's been going since. And then it just challenges students to consider minimizing their robot's weight and the energy consumption, and then maximizing the amount of dust tolerance and autonomy in their designs when they come up for the solution. Next slide, please. And then just a quick overview of the arena. So the robot will be randomly oriented in the left-hand side in the start area. And then from there, the robot has to move through the obstacle area and then into the mining area. And if you look on the right side, there's a figure. The circles represent regolith. And as you can see, it's a lot more densely packed down below 30 centimeters. So then once mining that, they have to go back through the obstacle area and then deposit the regolith that they gathered into the dump bin. Next slide, please. So here's just a quick CAD design of our robot, or our plan right now. As you can see, we have the bucket that has mesh, so the regolith stays in the bucket, and then all the dust and dirt will ideally fall out of there. And then we have two cameras on the sides, and then these are for position and orientation of the robot. And then at the mining section, we decided to go with a belt and bucket design. So the belt will be spinning around with little buckets on it, which will then be dumping into our big dump bucket at the back. And then we have control boxes scattered about the robot. Next slide, please.
My name is Alden Truesdale. I am also on the mining sub-team. And actually, if we can move this slide back by one, please. Over here in figure C, we'll actually get a look at what is going on underneath that mining belt that Kyle was talking about. Here we've got an inner chassis, which houses the drive motor and the drive and idle shafts or axles. That's going to all be contained within this inner chassis here, which will be brought up and down through that regolith to ensure that we get to that 30 to 45 centimeter depth limit by these lead screws. So pretty much this whole inner chassis system will travel down and then come back up. In figure B, we see how the linear actuator kind of can bring the belt system to it from its storage position and to its mining operation. And figure A would actually be pretty much how the robot would look while it's mining the regolith on the moon. And if we go to the next slide, we'll see the dump bucket that the conveyor belt would say be dumping into it. On the sides and the bottom of the bucket, we're going to have a nice kind of fine grade mesh. That mesh is going to be small enough so that we can hold the regolith inside the bucket, but large enough so that the sand and all the small dust kind of falls through it. If we're mining on the moon, we want to minimize the weight of the robot when it's traveling to and from that mining area. So any sand that we can deposit that we know isn't going to be worth our while to collect, we want to make sure that falls away and we're not carrying that weight to our dumping zone. Over here in figure B and C, we'll see the linear actuator that actually dumps the bucket into the dumping area so that we can collect our points and dump that regolith into the weighing zone. And if we go to the next slide, we'll see the last major component piece of our chassis, and that's going to be the wheels. Navigating on the moon, obviously, we've got some really fine sand up there. We're being graded on both the dust tolerance of the robot and just kind of how well we can maneuver within that dust. So here we've got a wheel that's built up of 3 pieces. We've got the outer 2 edges and the center column. And pretty much we're trying to sandwich as much dust and sand within our wheel so that we can kind of maneuver the best while we're trying to overcome these obstacles.
Awesome. And for the positioning system, which will allow us to figure out where the robot is, we've come up with two different solutions. So on the left here, we're using 4 wide-angle field of view cameras to look for barcodes that we've placed on the dump bin. And we're using that to calculate the position of the robot based on the size of the QR codes and the distortion. And on the right is a picture of some ultra wideband modules that we are using to communicate with some beacons that we've also placed on the dump bin. And they're able to measure the distance between themselves and each one of the beacons. And we can use that to calculate the position of the robot. So both of these together allow us to accurately localize the robot into the field. And we should be able to do some pretty good autonomy stuff with this. And for the rest of the control stuff, we're planning on having sensors on every moving part so we can tell where everything is. And ultimately, this all goes to our goal of being able to complete the entire competition autonomously, which gives us a large number of points. So we're using encoders on the wheels to track the position of the wheels and calculate the distance that it's driven, and we can air check that against the cameras and against the ultra wideband modules. And the people that are controlling this robot are actually sitting in a room that is separated from the competition. So they can't see the robot, they can't hear the robot. They're who knows where, you know? So I hope this gives you a kind of overview of what our project is and what the competition is. So if you have any questions, feel free to contact any of us and we can get that sorted for you. So thank you.
Awesome. Thank you, NASA Robotic Mining team, for presenting. We will now have Riff Raff Solar Hydronic Heating present, and Annalisa will be presenting on behalf of her team.
Hey everyone, my name is Annalisa Huns and I'm the project manager for Riff Raff Solar Hydronic Heating. So Riff Raff's a little bit different than the projects that you heard about earlier. We're a lot more focused on, instead of NASA being our sponsor, it's going to be one local business down in Southern Colorado. And if you go on to the next slide, you'll be able to see that here pictured as Riff Raff, we're able to go down and do a quick trip and tour the brewery and understand what our sponsors look for. So Riff Raff is a small brewery in Pagosa Springs, Colorado, and it's completely devoted to making earth-powered beer. Over the past few years, the business has expanded from the center of town to the second location that's pictured here, that's closer to the Rio Grande River. While this is a great spot, beautiful location, there's a big issue because they used to be able to tap into their geothermal line in Pagosa Springs, but they're too far away from town, so they can't do that anymore. And our entire challenge is to be able to keep up their earth-powered beer mantra. So we came in and this project was initially pitched to last year's team and they set up a foundation for us, but because of COVID, weren't able to continue. So my team was asked to expand upon last year's design and find a way to heat up the water that they're going to use for brewing while reducing the need for natural gas. So this is going to keep their business green and keep their beer earth-powered. And hopefully by the end of the semester, we're going to be able to give our sponsor a proof of concept prototype, which is something that I'm going to go over in the later slides, and a full-scale design so we can implement sometime in the near future. Because of all of the COVID regulations and the small business loans, he may be able to do it this summer, which is putting a little bit of a deadline that makes everything more exciting. If you go on to the next slide, I'll go through and talk about the prototype a little bit. So instead of making it all earth powered, my team decided to cheat a little bit. Instead of using the earth, we're going to use the sun. The premise behind these hydronic rods, which you can see are those black rods pictured to the left, it's almost ingenious. There's a special liquid within the rods that when heated up by the sun, it evaporates and rises to the top of the panel into the heat exchanger box, which is pictured. And then as that's happening, there's water that's flowing throughout the system, and the water goes through that heat exchanger up top. And the heat exchanger takes that heat from the special fluid and transfers it. The water then goes to a storage tank that is pictured just behind that wooden panel in the top left picture. And then the cycle is repeated continuously until it reaches a high enough temperature to be used. The really wonderful thing about this design is that it can be used indefinitely as long as it's sunny out and create little to no emissions. The only energy that we need other than sunlight is electricity to power the pumps. Although the prototype is working as planned, there's still a handful of problems that we're working on ironing out. The first, and arguably the biggest problem, is the reduction in efficiency due to the addition of glycol in the system. We decided to add glycol, which reduces the freezing point of water into this water side of the system because Pagosa is known to reach -20 degrees Fahrenheit during the winter, and a system would freeze would cause catastrophic failure, which is pretty much the last thing that we would ever want. So the team, in addition to adding the glycol and trying to fight with that back and forth, is also focusing on adding insulation wherever we can to continue to lower the glycol percentage and increase the overall efficiency. So this picture shown at the far left represents a solid model of our proof of concept prototype with 3 main applications for the brewery, represented by the buckets to the right. At the time of drawing, we believed that the hot water would need to be diverted to a hot liquor tank, a snow melt system, and domestic heating throughout the building. After talking with our sponsor and kind of fighting back and forth for a couple months, we discovered that the plumbing doesn't actually allow us to tap into the last 2 applications, and there's a central boiler that we need to tap into otherwise. So that changed pretty much our entire design, and we're really focusing on being able to send all of the water to the hot liquor tank, which will truly make the earth-powered beer and make everything green. So on brew days, which is going to be the biggest application, the hot liquor tank goes through hundreds of gallons of water and puts a major strain on the natural gas boilers that they use to heat it. And being able to supplement all of that with a hydronic system will reduce their need for natural gas and therefore make the project a success. So in addition to adding these panels, we're also going to tack on a control system that's going to be able to function inside the brewery. It's going to be able to divert water and make sure all the temperatures are within the healthy ranges for the boilers and stuff like that. For our proof of concept, we're going to be putting our control system directly onto that wooden panel shown. And after the big change in design, we discovered that the control system, instead of being highly complicated like the ones that you're doing with the like the robot that we just talked about, it's instead going to be highly focused on pumps, valves, and what we like to call a glorified floaty. The floaty is going to be inside the hot liquor tank, and like the one that you have in the toilet. So when you flush, it goes down, and once it gets the water level, the water stops draining through. And that's going to be the basis for our control system. And then, as you can see in the other picture, that's our physical prototype that we're using for testing now. And we're using a fairly large storage tank, which isn't pictured here. And by storage tank, I mean a 50-gallon trash can, but nobody needs to know it's a trash can. It's definitely a storage tank. And we're able to reach temperatures of over 100 degrees Fahrenheit with that 50 gallons. If we were using a smaller storage tank, we'd be able to reach higher temperatures, which we tested to be about 140 to 160 degrees. But because of the high volume applications in the hot liquor tank, it's going to be a better representation if we stick with trash can. So this difference between the high volume of warm water versus a low volume of hot water has proven to be the most difficult design consideration. And it has required a lot of conversation, a really deep understanding of the project's goals, and how we tap into the plumbing. So if we go into the next slide, I'll talk a little bit about the full-scale model and why we decided to use the prototype. So the best part about this prototype is that we're putting in the majority of the work right up front, and we're going to be able to directly scale it all the way up to make it a truly good proof of concept for the full-scale system. So my team needs to understand the efficiency of the system through testing and then implement thermal analysis to figure out how many solar panels we need for the brewery's applications. As of right now, we're designing the system to have about 18 panels due to the roof size, but there needs to be an economic consideration as well. Does it, at some point, it's going to be not enough return for how much he's spending, and because this is a real business, we want to make sure that we're providing him the best design possible. So that being said, the analysis portion is definitely the heaviest part of the entire project, but it is completely fundamental to our success. We have to understand how the brewery functions, the changing angles of the sun, and the thermal properties that go into the working fluids that I discussed earlier. The thing that I really enjoy about this project is that we're able to apply everything that we learned in class to a real world business and take all of these heat exchanger ideas and apply it in a very tangible sort of way. Everything we've done up to this point has been very, very theoretical and filled with assumptions that are not possible out of the field. This is kind of the idea that if you ignore air resistance, it's really nice to do your calculations, but really bad if you try to send a rocket somewhere up. So the difference between like riffraff and some projects mentioned earlier is that our constraints are like the roof size and the budget, and it's because we're messing with a real business. We don't want to do anything that could potentially damage them in the long run. And then with all this considered, this project is really fun, applicable, and focuses on sustainable business, which is something that I'm really passionate about. I feel very grateful to be a part of this team. Riffraff is a wonderful example of the possibility to be successful and still be environmentally conscious. And just to divert a little bit, I wanted to show talk about the freedom of being a mechanical engineer and being able to talk about aerospace and mining projects and breweries and implement all of that. And I'm more than happy to answer any questions at the end of this. So thank you.
Awesome. Thank you so much. We'll now have Justin talk about RAM racing at the CAE.
Hi, everyone. My name is Justin Falk, and I'm the project manager this year for Formula SAE, the Society of Automotive Engineering. And just a little bit of background, FSAE is a program where you design your own Formula One style race car. And at the end of the year, you drive out to Nebraska and compete against up to 200 other colleges across the nation in a series of events to see who built the best car. And to use 3 words to summarize what we do at FSAE is envision, create, and test. So we can go on to the next slide. Starting with envision, it's what we do most often as engineers. It's the planning stage where you get all your ideas out, you run calculations, you create solid models. And you can see examples of our solid models, such as the chassis rendering and the engine model. But as you all know, a car is more than just a chassis and an engine. With regards to the suspension this year, we're running inboard pushrod actuated double wishbones, both front and rear, to increase the stiffness of the car and hopefully the overall performance. The chassis is a lightweight steel space frame, and then it's going to be wrapped in carbon fiber with carbon fiber aero components. This was done, 1, for structural rigidity, 2, to maximize the internal space for both the driver and other components of the car, and 3, to just give us as much design space as possible. The engine we're using is a motorcycle engine, an R6 to be specific. It's a 4-cylinder engine that we're hoping to rev right around to 10,000 RPM at its maximum, creating around 75 to 100 horsepower after the throttle restrictions and over 100 pound-feet of torque. And if you don't know a lot about horsepower and cars, this thing is going to be really quick. Think basically a go-kart on steroids. All of this is well and good, but without prototyping, it's hard for us to actually test what we want without wasting a ton of money, which is why we use 3D printing for rapid prototyping for things that aren't critical, such as like the intake manifold, to just test some airflow. You can go on to the next slide, please. After we're done with our design process, we go on to the actual creation process of our car. And the majority of this, at least for the chassis and suspension parts, is welding. It's how you stick two things together that you don't want to come apart. The majority of this project uses MIG welding, which is faster than TIG welding, but TIG does have certain advantages. To do some more precise work, we use machining, such as milling machines and lathes, and we will be using CNC for some more complex parts later down the line. To get things like the shape of the body and some other non-essential components, such as the firewall between the driver and the engine, we do use sheet metal bending and different forming techniques to create the exhaust car. This year, we chose for our chassis setup, like I said before, to run the double wishbone suspension. This gives us great flexibility for a variety of factors, such as the camber, the caster, the front and rear ride heights, the spring rates, the weight bias front and rear of the car. All of these were taken into consideration for us to be able to create the most competitive car, working off of disadvantages we saw when analyzing the data collected from last year's project. Another key component of creating the most optimal car is engine tuning. You can see one of the spark tables on the top. It's the really colorful one. Spark tables allow us to influence how the engine acts at certain rev ranges. It allows us to create a lot of power down low, a lot of power up high, whatever we want. We can make it happen with a spark table, different timing, fuel flow rates, all of that stuff. So far, like I said earlier, we are aiming for around 75 horsepower, and we want that to be optimized over the entire rev range. So we do that with our spark tables. You can go on to the next slide, please. And finally, the testing phase. Once everything has been envisioned, everything has been created, and it's all put together, we have an on-site test track. There's an abandoned airfield out next to the ERC where we can do top speed tests, handling tests, all sorts of different tests that we would see at competition. We can test them at our facilities, make changes on the fly, and sort of optimize our car to the next level. Like I said at the beginning, there are different events at competition where you compete against hundreds of other schools, both static, dynamic, and design events, such as like a figure eight test, top speed test, drag races, handling around a circuit. And there's even tests for how well you designed your car, because you can go out and just buy all of the parts yourself, or you can do the engineering route and hand design them all, which you get extra points for. And one of the other key things that we touch on throughout the entire process is driving techniques, because the FSAE team, we drive our own car, and not everyone has driven single seat race cars before. We do have a racing sim out at the ERC, which we use to help teach people the proper racing line, braking points, tire management, fuel wear, what to do in like dangerous situations, because these cars, you can see from the photo, are extremely fast and can be extremely dangerous. But hopefully through perfecting driving technique, that never actually happens. I believe that's it for our presentation. If you have any further questions, feel free to email me at justfalk@rams.colostate, or you can get in contact with Dr. Weinberger. Thank you.
Awesome. Thank you so much. I just want to thank again all the presenters who presented today. I think it's awesome to be able to just hear about all the different projects that they're doing and all the different details that go into the projects. So thank you so much. We now have a few minutes to have any questions that students might have. If you have any questions, feel free to raise your hand and then I could unmute you and then we could ask those questions and see if the presenters could answer those for you. Okay, well, if there's not any questions, like the group project presenters said, feel free to always reach out if you do have any questions. One thing I always kind of encourage incoming students is definitely get involved. Getting involved, with these different projects is something that is really nice because then you're able to kind of learn valuable information and kind of get that hands-on experience. And so definitely just thinking about that before kind of joining the program or whatever you end up doing, kind of thinking about volunteering and getting involved with different projects on your campus. So thank you so much for joining today's session. We'll go ahead and end the meeting today. Rachel, is there anything else that you wanted to add? Awesome. Okay, then I think we're good then. Yeah, thank you all for helping. Again, presenters, thank you for joining us and presenting. And for those who joined the group session, thank you. We hope you enjoyed it.